our FlashTalks. So let me remind you again how this format works. We will now have 3 FlashTalks. Each will be around 10 minutes long, and we will not break for questions in between those, but we will have a 1 question and answer block at the end. So these will be a little bit less on topic, let's say, but for this high throughput and machine learning database stuff. But nevertheless, we are very happy to have our Flash talkers here and to provide opportunity to speak in this format. And the first one, already I see that some cameras are getting activated. So the first one will be given by Nusrat Chowdhury. I hope I did not pronounce this too wrong, from the University of Illinois. And afterwards, I will just try to pronounce all the names now. After her, we will have a talk from Fakhrul Hasan Bhuiyan, Bhuiyan from UC Merced, also from the US. And then we have Alberto Pacini, who is actually working with Clelia at the end. So, Nusrat, if you have already unmuted yourself, if you can share your screen, she will, yes. So we're a little bit early, so don't start yet. It's only at least on my clock, it's 2 minutes to 3. So I think if there's someone who is just interested in the Flash Talks and had not joined our YouTube stream so far, I think we should delay by 1 more minute. But it's good that you're ready. If you, yeah, I will give you a sign when it's time to start, and then I will give you also if you can make sure you have the chat open. I will give you a small reminder if I feel your time is running out, so that you can come to the conclusions in 1 or 2 minutes. Okay. I will do that in a private message in the Zoom chat. So, I think with the edit delay that we have on YouTube, now it's time to start the Flash Talks. So, Nusrat, please go ahead.
Yeah. Hi, everyone. I'm Nusrat Chowdhury. Today, I'm going to talk about neutral hydrogel permeability as a function of fluid viscosity for robust low friction application. So, let's start. So, what is hydrogels and why do we need hydrogels? So hydrogel is a cross-linked hydrophilic polymer that does not dissolve in water. So the potential use of hydrogels is like it can be a potential replacement for biological tissues like articular cartilage, and also it is used in contact lenses. Many researchers have tried to find the permeability of hydrogels because of the surface properties are related to the structural and chemical properties of hydrogels. So earlier researchers have tried to find internal properties like mesh size, concentration, and pore size, this type of relation with permeability. But there is not so much work on the surface properties relation with permeability. However, that is why we hypothesize that there is an explicit connection between permeability and lubrication because of the biophysic nature and low friction hydrogels. So in the current effort, we try to find the relationship of permeability with viscosity and also the relation of permeability and friction coefficients. So what is permeability? Permeability is a unit of measure that describes the mobility and ease by which fluid can navigate. So if there is a membrane, it is the measure that how much water or fluid can flow through that gel. So it is denoted as K on Darcy law. So there are various types of application of permeability: transport of molecular penetrance, drug delivery in biomedical and pharmaceutical companies, nanocatalysis, and lubrication mechanism. And we are trying to work on the lubrication mechanism side of the hydrogel and its permeability relation. So this is the experimental setup for our permeability tester. So the main variables where we set the pressure at varying from 10 to 30 kPa, each at 5 kPa intervals, and the viscosity of was 0.001 for a specific test. This one is water, and the gel thicknesses were 0.45 millimeter, and the hydrogel concentration of acrylamide concentration was varied from 7 to 11% for varying concentration tests. Though the setup looks very complicated, it is not. We just supplied controlled pressure through this line, and the water was flown from here to the gel holder where the gel was situated. So after flowing through this gel, the water was collected in a pot, and with time, the volume flow rate was calculated. And we measured the velocity from that volume flow rate, and with the help of Darcy law, we found the permeability of the gels. So after that, each gel was tested for 5 times at each pressure, and pressure was varied from 10 to 30 kPa for each concentration, and each concentration was tested like with 3 gels. So there was a total of 15 tests for each concentration. And from the velocity values, I showed you how we found earlier. We plotted the velocity versus pressure plots for each experiment and found the experimental permeability value with fitting this with a linear fit in the graph. And additionally, we did was applied Monte Carlo simulation, where we did uncertainty analysis for both x and y, velocity and pressure values, find ranges of x and y error bars, and applied different types, taking random values from that limits of x and y. We applied linear fit several times. For your visual clarity, I showed 5 runs of Monte Carlo simulation and their slope values and the confidence. And for reaching 95% confidence, we did 100,000 simulations of Monte Carlo simulation and find a precision up to 0.3 decimal places. So I just showed the 5 values. And moving on to the main part, and moving on with the results, we plotted total polymer concentration in the graph in the x-axis and the permeability values. So the total polymer concentration was varied from 7.45% to 11.45%, keeping the monomer by crosslinker ratio constant at 25. So the main takeaway of this graph is like the permeability has a definite concentration that does not vary much, and with increasing concentration, with increasing monomer and crosslinker concentration, the permeability is decreasing. Why is that? The higher the monomer crosslinker concentration, the higher the polymer chains will be closer to each other, and it will be hard for the fluid to flow through that gel. So that is why the permeability decreases with the monomer and crosslinker concentration. So another takeaway of this graph is that with a very few experimental values, we can get more precise Monte Carlo simulation prediction and get a more precise permeability values. And also we can predict that permeability values from the Monte Carlo simulation, and the concentration we tested also at different concentration, we can predict the permeability. So, and moving on to viscosity relationship with permeability. So one of the papers from our lab found that there is a surface property friction coefficient have a relationship with permeability and viscosity. So in the relationship, you can see the friction coefficient has relation with permeability and viscosity. So there is also, so in the graph also, this graph is from the paper. So the friction coefficient versus speed into viscosity has a like a lubrication regime. So we are assuming there is some friction un- underlying mechanism working on it. So as the Darcy law has also relationship with permeability and viscosity. That is why we are trying to find viscosity relationship with permeability. So for this, we are using DMSO in our experiment. We just use the same experimental setup, but substituted water with DMSO now. And the viscosity of the fluid was varied by varying the concentration of DMSO in water. So the experiments are ongoing. We hope to find some valuable findings from these results and present you in future. And moving on to the friction coefficient relationship with permeability. So in a past paper from our group by Real, friction was shown to have control or by how much water is in the gel in the area of contact. So that is why we are predicting that permeability is an important parameter in defining friction coefficient. So in the graph, you can show that, see that friction coefficient and versus Peclet number is shown. So what is Peclet number? Peclet number is a ratio of advection by diffusion. So the higher the diffusion, the higher the Peclet number will be. So in the graph, they found that with higher Peclet numbers, the friction coefficient decreases. So we are predicting that there would be some relationship of permeability and friction coefficient. As you can see from the equation, the permeability is a direct parameter of Peclet number. So these experiments are also ongoing, but we hope to find a direct relationship of permeability and friction coefficient in future. Thank you. Let me know if you have any questions.
So thanks for the first presentation. Questions, as I said, will be done afterwards. So with that, I would ask Fokrul to share his screen, please. Okay, and please go ahead with your presentation.
I hope you can see my screen.
Yes, we can see it well. We can see you. We can hear you. Maybe you can just start. We are perfectly in time.
Okay, sure. Got it. Nice. Hello, everyone. I'm Bhuiyan, a fourth-year PhD student in the Martini Research Group at University of California, Merced. Today, I'll be talking about our study on tribochemical reactions of simple organic molecules at a sliding interface using reactive molecular dynamic simulations. Recently, it has been shown that many application-relevant tribochemical reactions are assisted or driven by mechanical stresses available at a sliding interface. But how do mechanical stresses drive such reactions, and what are the molecular mechanisms? Here, today, I'll try to answer these questions, but first, let's start with tribochemical reactions. Well, as you may know, almost all tribological systems involve some chemical reactions that are commonly known as tribochemical reactions. These reactions can be association or dissociation of these interfacial molecules, or reactions between these molecules and the surfaces. Such tribochemical reactions can lead to either material removal or wear, or material accumulation, such as tribofilm formation. And many of these reactions, in fact, do not happen naturally without the application of sliding motion. Tribofilm formation specifically has been shown to be driven by mechanical stresses. And tribofilm is critically important for the efficient function and durability of machine components because tribofilm reduces wear and friction, especially in the boundary lubrication regime. But what is the tribofilm? Lubricants, among many other additive molecules, contain small amount of anti-wear additive molecules such as ZDDP, TCP, or MODTC. During operation, these additives can react with the surfaces of the machine components and create a protective film on the surfaces. This protective film, which is also known as tribofilm, reduces friction and wear by minimizing solid-solid contact. So from no film to tribofilm growth, tribofilm forms through some mechanism. Three key components of film formation are the physical and chemical composition of a tribofilm, the reaction mechanisms that lead to that film growth, and how different operating conditions such as heat or stress affect these film forming reactions. To fully understand tribofilm formation, we have to discern the individual contributions of all three components. And for that, we have several research tools available at our disposal, such as theoretical framework to model film forming reactions or different experimental techniques in macroscale and nanoscale to study film growth. Although these research tools have done a great job to elucidate these mechanisms, there are some key questions that still needs answering. For example, how heat, pressure, or drive tribofilm formation, and what are the differences between the shear-driven pathways or mechanical reaction pathway and the thermally driven reaction pathways. What's the difference between the contribution of normal stress versus shear stress, and how does molecular structure affect susceptibility to mechanochemical activation? We believe that computational techniques such as molecular dynamic simulation is a powerful tool that can be effectively used to complement the theoretical framework and the experiments to fill in the blanks. As such, we used molecular dynamic simulation with reactive force field to simulate alpha-pinene molecule in between two silica slabs. Reactive force field can capture chemical dissociation and formation, which allows us to study the chemical reactions happening at an interface. We performed three types of simulations: a heating simulation, a compression simulation, and a sliding simulation. We then tracked the chemical reactions that happened in these systems. The two key reactions that we looked at are oxidative chemisorption and oligomerization. For the oxidative chemisorption reaction, you can see an alpha-pinene molecule reacts with a surface oxygen atom to become oxidized. And for an oligomerization, two alpha-pinene molecules react with each other to form an oligomer or dimer. And as you can see, in both cases, the surface oxygen atoms or the surface plays a key role in these reactions. Interestingly, we observed that the oligomers formed at high temperature. In heating simulations formed at very high temperatures, and no oligomers formed in just by compression. However, significant number of reactions happened in the sliding simulations at room temperature. This means that shear is a key driver of these tribochemical reactions. We then analyzed the reaction pathways that led to oligomer formation and found multiple such pathways. In pathway A, the double bond site of both reactant molecules were activated to form the dimer. On the other hand, in reaction pathway B, the four-membered ring was activated which then got oxidized and then reacted with a similar molecule to form an oligomer. Interestingly, both pathways were accessible through shear stress or mechanically, but only reaction pathway B could be activated thermally. This suggests that the mechanical stress-driven pathway and the thermal reaction pathway of the same reaction can be different. This also suggests that the chemical features of a reactant can play an important role in the mechanical activation. To further understand the effect of different chemical features of a reactant in their mechanochemical activation, we simulated three simple organic molecules: methyl cyclopentane, which has a methyl group side chain; cyclohexane, which is a 6-carbon cyclic molecule; and cyclohexene, which is like cyclohexane but has a double bond. We compressed and sheared this molecule at a silica-silica interface and then tracked the oxidative chemical reactions. In this molecule versus simulation time plot, the darker blue represent the change in the number of precursor molecules in the simulation, and the lighter blue represents the oxidized molecule in the system. And as you can see, methylcyclopentane and cyclohexane were not that sensitive to mechanical stress as they remained fairly unreactive. However, cyclohexene was very sensitive to shear stress as it reacted vigorously as soon as we started the sliding process. But what is causing this significant difference among these molecules? To answer that question, we numbered the carbon atoms of the molecules from 1 through 6 and calculated the probability of each of these carbon sites to participate in an oxidation reaction. The result is shown as a pie chart. Looking at methylcyclopentane and cyclohexane, it looks like all carbon sites of the two molecules were more or less similarly reactive as they have similar probabilities of going through an oxidation reaction. However, cyclohexene is completely, again, different as most of the oxidations happened at the double bond site, which is the C1 and C2. This suggests that the carbon-carbon double bond is more susceptible to mechanical stress. We also looked at the number of oligomers formed in our system and found that cyclohexene formed the highest amount of oligomers, while the other two formed only a few oligomers. Since oligomers are the first step towards tribopolymerization, we compared our results to ball-on-flat tribometer experimental results of these precursor molecules, and we found a qualitative match. Since cyclohexene also produced in the experiments also produce the highest amount of tribopolymers. And finally, we analyzed the oligomerization reaction pathways and found out that methylcyclopentane and cyclohexane followed a similar reaction pathway that involved hydrogen elimination, then oxidation, and finally oligomerization. Cyclohexane followed a slightly different path, which involved direct oxidation at the double bond site followed by oligomerization. In conclusion, we observed that tribochemical reactions can be driven by mechanical stress, and these type of reactions are also known as mechanochemical reactions. By modeling such reactions using reactive in the simulation, we tried to capture the atomistic details of mechanical activation of these molecules. Our simulations enabled the isolation of the effect of heat, normal stress, and shear stress. And we found that shear stress to be critical in driving these reactions. We systematically studied different organic molecules to capture the effect of different chemical features on mechanical activation and found out that carbon-carbon double bond can be quite susceptible to shear stress. That's it. The main point, the takeaway point is that simulations can show how chemical structure affects the mechanism of and susceptibility to mechanical activation. With this, I'd like to thank you all. And this is a published work that you can find here. Thank you.
Thank you very much. Very nice talk. Again, questions will be asked later. So please, Alberto, if you can share your screen now.
Share the screen. Okay. Okay.
Perfect.
Okay.
And we are still perfectly in time.
Okay. Welcome, everyone. I'm Alberto Pacini, working at Cagliari Viscosity group at the University of Bologna, together with Gabriele Rosi, the previous member of the group, and in collaboration with Nobuaki Kitawa and Seiji Kajita at the Toyota Center of Lab in Japan. And we developed a new multiscale method which links together ab initio and Green's function molecular dynamics, and we applied it to study diamond interface. I would like to recap ab initio molecular dynamics. So we start with an atomic configuration, then we have to solve the Kohn-Sham equation for the electrons. We find the electron density, which in turn gives us the force that acts on the nuclei. And then upon integrating this equation, we get the new nuclear configurations, and updating that, this is a classical, let's say, ab initio molecular dynamics loop. So we have described what is called the Born-Oppenheimer molecular dynamics. The problem is that this equation has to be solved at every iteration, so it's computationally expensive. Another approach is the Cardinal molecular dynamics. This equation is just solved at the beginning, and then the orbitals are just propagated in time together with the nuclear coordinates. So it's much faster. Now, in our case, we want to study sliding interfaces. So this sliding induces vibrations at the interface that then propagates into the bulk. And in order to capture this vibration, one needs a large number of atoms. And this is a problem with ab initio molecular dynamics because it scales with the number of atoms. And so we rely on multiscale approaches. And the idea of multiscale approach is very simple. We divide our system in two parts, one chemically active and one like a reservoir region, which is simulated classically. Now, in our case, this splitting is quite natural. So the interfacial atoms will be simulated ab initio, and the bulk atoms will be simulated classically. But then we want to simulate actually a semi-infinite bulk. And this is a problem also for classical molecular dynamics because we have an infinite number of atoms. So we rely on the Green's function approach, first devised by Martin User. And the idea is to use this Green function to project the dynamical response of an infinite number of atoms onto a Green function atomic layer. And this is, let's say, a convolution integral which exploit this Green function and give us the response of the bulk atoms. Now, to intuitively understand what is the Green function, so let's imagine to poke a system with an external force. This force will propagate inside the material and displace atoms in a complicated way. But this is governed by the internal dynamics of the system. And the Green function can be seen as a response function which links the input, which in our case is the forces that the quantum mechanical atoms at the interface apply upon the bulk atoms, and the response, the output, which is the bulk atoms displacement. Upon some approximation, we can derive an equation that the Green function has to satisfy, which depends on some parameter of the bulk, which are elastic parameter of the bulk, which can be calculated via ab initio phonon calculation. Now we can overview the method in brief. So we start with a bulk. We perform phonon calculation to get the internal force matrix, which allows to, let's say, to get an equation for the Green function, which is then computed, and then we can use it inside a standard molecular dynamics loop. And the idea is just that instead of directly evolving in time the quantum mechanical atoms, we first perform the convolution integrals to take into account also the dynamics of the Green function atoms. We apply our setups, our GFCP molecular dynamics, to study diamond interfaces with different degrees of passivation under tribological conditions. And what we observe is that at zero coverage, we have a graphitic layer, which is formed at the interface. With 25% coverage, the system remains stuck, so it doesn't not slide for the applied lateral shear. Whereas for the 50%, 75%, and full coverage, we have sliding, and we focused on the dynamics of these systems. So we report the time average of the derived from the dynamical results for these three systems. So we applied first 1 gigapascal of lateral shear. This gives rise to these sliding velocities, but the important fact here are the friction forces, which shows a decreasing trend with increasing hydrogen passivation. So, and also this is reflected in the kinetic friction coefficient. Then we repeat the same analysis also for 5 gigapascal of applied lateral shear. Now the velocity is increased also almost to 300 meters per second. And we see an interesting behavior of the friction force, which for the, let's say, systems which possess the most coverage of hydrogen, we have the friction force which decrease with the lateral velocity, with the applied shear. And we want to further investigate this fact. So what we have done is we take our interface and we perform static calculation to get an adhesion energy map. And we know that the minimum energy path is a property of the potential energy surface. And then we start the lateral shear, and we record the relative trajectories upon the potential energy surface for both the sliding regimes. And we perform this analysis for every passivations, and we get these beautiful plots. And we can see that at the low applied shear, the systems tries to follow the minimum energy path. Whereas for higher applied shear, the system, actually the trajectories do not resemble the minimum energy path. It's much straighter. So we know that the potential energy surface induces forces by taking just the gradient of the potential energy surface, and we project those forces along the trajectory. So we perform this projection for the 1 gigapascal shear, and we get this graph. So we can recognize this characteristic sawtooth profile, which is characteristic of stick slip regime, in which we have a stick phase where an accumulation of elastic energy is occurring. And then we have a slip phase where this elastic energy is released. And through phononic dissipation, we lose, let's say, energy, kinetic energy, and we get a net friction force, which is indicated by this average here. Then we repeat the same procedure for 5 gigapascal of applied shear. And we see that in this case, we are in a continuous regime where there is an efficient force compensation because the systems are sliding over the potential energy surface and are not very affected by them. And there is an higher cancellation, and so a smaller net friction force. Then this is the real, let's say, forces coming from the dynamical simulations. And this is a very noisy signal because of thermal fluctuations. So we perform a Fourier transform, and we analyze the low frequency region of the spectra. Why we do that? Because we know that there is a relevant frequency, which is called the Washburn frequency, which is given by the sliding velocity over the lattice constant. And in our case, we see that at those Washburn frequency, the spectra for the real dynamical forces are peaked and are similar to the PES-derived forces, which are peaked at the Washburn frequency. And furthermore, we see that there are all those peaks at higher frequency, which are related to surface modes because are common to every system, whereas at low frequency, we have interfacial modes which characterize the different passivations. So in conclusion, we developed a multiscale method which links ab initio and Green's function molecular dynamics, which takes into account both electronics and phononic degrees of freedom. And so this gave us the possibility to obtain quantitative estimates of kinetic friction coefficients, which are in agreement with experiments, and also describes known tribological phenomena like the effect of surface passivation and graphitization, and also to gain insight into the fundamental nature of friction. Thank you very much for your attention. If there are any questions,
thank you, Alberto, for this nice presentation. Also nearly perfectly in time.
Thank you.
So now, I think if you stop sharing, we can maybe see everybody again, at least the faces. And this time we have already some questions in the chat. So very nice that apparently the audience is much more interested in the FlashTalks then no, nothing against the wonderful presentation of Clelia, of course. So the first question that we got is from Stefan Peters, which is for Foucault. So second presentation. What is your opinion, the reason why shear is able to promote the reactivity of the molecules while load and temperature do not promote those? Or not in the same sense, I imagine.
Yeah, that is a great question, actually. And that is something that we're pursuing right now. From our previous studies, we have seen that shear stresses can deform molecules. So they can induce deformation of the molecules just before a reaction happens. And based on that result, we kind of suggest that maybe shear stress induced deformation make the molecules reactive. But that also, then the next question would be, why can compressive stress do the same thing? That right now I don't have a good answer to, but we have seen that compressive stress cannot really deform a molecule. Why not? I'm really not sure at this point, but yes, that's an ongoing investigation.
Okay, thank you. So second question is actually also for you. It's from Davide Sarpa. I hope I pronounced that correct. So, hello, amazing talks everyone. I wanted to ask Foucault if they tested the effects of film thickness on the promotion or demotion of chemical reactions.
Film thickness, we have not done that kind of study yet. Mostly we try to stay close to our experimental collaborators who are doing vapor phase lubrication condition experiments. In that cases, we expect a monolayer film thickness on the flat. So in simulations, we also try to simulate a monolayer film, but definitely we are interested to do thickness-based experiments and also changing the shear rate or sliding speed, the effect of shear rate or sliding speed in these reactions. That would be also interesting.
Okay. So then we have another question by Stefan, here. What is the effect of oxidation clusterization of the compounds on the tribological properties of the interfaces? Are they useful or not? So this is again for you.
Can you say that again, please? Sorry.
Okay. What is the effect of oxidation / clusterization of the compounds on the tribological properties of the interface?
Tribological properties, I think that's an interesting question. So from our results, we found that the oxidation is important to drive this tribochemical reaction. So to drive the tribopolymerization. We do not see tribopolymerization, but we see oligomerization in the simulation. But in the experiments, they see tribopolymerization, but they cannot see any process what's leading to that tribopolymerization. So based on the experimental result and the computational result, we suggest that these oxidation reactions eventually lead to tribopolymerization. So, they play an important role. But again, the oxidation, happens through surface oxygen atoms and the precursor molecules. So precursor molecules are reacting with the surface oxygen atoms, and during the sliding process, they can take that oxygen molecule with them from the surface, and that can lead to wear. And we have seen that in the experiments. So that also, through the simulation, we kind of found the wear mechanisms of that they see in the experiment. So yeah, that oxidation can also lead to wear.
Okay, thank you. I have a question, although probably not a very intelligent one for Nusrat, because I had really, this is really not my expertise, but you had in the beginning these lovely pictures of knees, and my knees are really bad. And I was interested in this hydrogel research that you do. How much you think, how many years is this away for actual this application of cartilage in knees, of artificial cartilage maybe? Because for me this will be very important in 10 to 20 years, I imagine.
Yeah, so there are various types of properties. So we know all work friction and lubrication and wear of this gels. So we are doing some um, we are doing some tests to see how biodegradable it is. So whether the permeability is changing with time or not. So far my gels are not changing with time, the permeability. So that's one type of findings we are doing, and also whether the friction matches. And so the lower the concentrations, the friction is lower, but when the concentration is higher, the frictions are higher. But in the our articular cartilage, the stiffness is also higher and the friction is also lower. So we are trying to replicate that type of things, which are very hard in real life, but it's presumably possible with hydrogels. That's why. So yeah, I think it will take 10 to 15 hours, years, and we are close to it almost. Yeah.
I think 10 to 15 years is for me a satisfactory time frame. That's my doctors give me that at least. Yeah. Okay, thank you. Then maybe I don't see. I mean, if there is anything else in the panel, anyone wants to ask a question?
Hey, sorry, my internet connection went down and I lost a couple of minutes. I had a couple of questions if we have time.
I think so, yes.
We don't have more questions in the chat, which I don't think we do. So my first question was for Fakro. So you mentioned you did shear simulations as well. How did you decide which velocity to choose? And you also mentioned you use the Reactive as a potential. Is there a problem with choosing given a shear velocity when you use Reactive as a potential?
Yes, thank you, Stella. That's a good question. The shearing rate or the sliding velocity that we used was 5 meters per second. That's usually, a common value to use in this type of molecular dynamic simulation. That's if we convert it to something experimental or experimentally relevant number, then that would be actually a pretty high value, pretty high sliding speed. But due to the computational cost and resources that we have to run at these type of values. And using Reactive, we haven't really seen any problems, I guess, with different sliding speeds or shear rates. Definitely a lower sliding speed would be, better, but I guess we can, I have seen even people using 10, 20 meters per second, and that was acceptable. So I haven't seen any problems in my experience yet.
Okay, thanks.
Thank you.
Last curiosity was for Alberto, but I don't know whether you guys have already asked something because I went down for like 2 minutes. I don't know
you're
what
fine.
happened. I was just curious in which framework combination of codes and methods you have developed your multiscale approach.
So the Carparinello is within the Quantum Espresso suite. And then there is, say, a preliminary part, which is written in Ruby, which basically takes into account the calculation of the green function, starting from the phonon calculation, always performed within Quantum Espresso. And then there is actually the link, which is written in Fortran, so is compatible with Quantum Espresso, which basically links, let's say, the pieces, and it is within the module in molecular dynamics of Carparinello.
Okay.
So it's Carparinello and let's say a Ruby external package.
Wrapper.
Yeah. Called
Okay.
Green Tea.
Okay. Cool. Thank you very much.
You're welcome.
So maybe I have not really a question, but kind of discussion opportunity maybe within the panel, because I'm not really a molecular dynamics guy myself, but I would be interested in a discussion between Alberto or some comments by Alberto and for Carlo about different ways of running this. Like this, as far as I understood, this greens function method kind of alleviates the use of a thermostat. Or
yes.
Yes. So maybe you can comment on the advantages of using more traditional methods to thermostat a system like this, tribological systems, or the advantages of doing this with this green function method. So
Yes.
so I would love to have comments by both of you on this. Thank you.
Yeah. Let's say the thermostat are present within the let's say the bulk region. So they are taken into account by the green function atoms. And the way to do that is basically to initialize the velocity of the bulk atoms in such a way to be compatible with the temperature that you want. And then also the green function takes into account the shear, for example, and the applied load. So basically, you set the thermal conditions and the barostat by setting the initial condition for the green function atoms, which are subjected to an harmonic dynamics. So basically, there is a dynamics which takes into account the response that they have to do with respect to the interfacial region. And there is a free dynamics which takes into account the initial conditions and gives you the opportunity to set the thermostat and bars. So basically, it's within the green function. So the interfacial atoms are not thermalized. I mean, they are thermalized because of the interaction with the green function atom, which represent the bulk.
Okay, that's nice. I can say from my perspective, the way we thermostat our system is probably somewhat, I don't know, can be different, because usually, as Alberto said, thermostats are done at the bulk or at the surfaces. In our shear or sliding simulations, if we want keep the temperature constant, we have to thermostat the molecules too. Otherwise, because in the experiments, they can calculate the increase in temperature, flash temperature at the interface, and in their cases, the increase in temperature is quite negligible. So in our system, we try to do that by thermostating the molecules, the interfacial molecules themselves too, so that during the sliding process, that temperatures don't fluctuate too much or increase too much due to the sliding process.
Yeah. So yeah, as I said, in our case, you leave the interfacial region without the thermostat, and during sliding, clearly you have energy dissipation into the interfacial region, which is then transported away from the interface through the bulk, and this is done definitely with the coupling of the green function. And clearly, this effect of the thermalization is kind of physical, because you are effectively simulated an harmonic bulk. So you take into account the effect of thermalization in an harmonic way. So okay, first order approximation, okay, of something which has to be.
Okay, thanks. With that, I think we have taken our time that was allotted for questions. We have, if somebody has more, we can do that. We have scheduled a 50-minute break, however, which I kind of have to use to go to the bathroom. So if there are no more questions, I think we keep the string going. So also your will